Okay, so Friday. Last time we did section 3.1, right? We started kind of learning how to use our calculators. We're going to do a lot more of that today. Any questions over 3.1? That homework is due tonight by midnight, right? And, yeah?
Yeah, I have a quick question over 3.1.
Okay.
So, for this skewed graph going left.
Okay, skewed left. Yeah?
How would you able, which one would be the
Oh, okay, I know the kind of question you're doing. It looks like this. A, B, C.
Yeah.
And they have homework questions that say which one of these would be the mean, the median, and the mode.
So, like, I can tell if the mode is C and the median is
Okay, good. The mode is C because the mode means
this mode.
most common observation, so the tallest peak, right? And then what happens, remember we had the little example where we showed what outliers do to a mean? Thank you. What happens to the mean when you have outliers? The mean gets pulled in the direction of the outliers. So a skewed left will have outliers out here. So the mean's going to get pulled that way, but the median, not so much, right? So B will be the median, A will be the mean. It's further out. Okay, so this will be the mean, and this will be the median. If it were skewed right, then they would reverse. Okay? Any other questions? All right. Well, today we will do section 3.2, which is measures of dispersion. That's a big $40 word. What does dispersion mean?
Spread out.
Spread out, right? So I like to say measures of spread. How much spread is there in the values in this data? Okay? So sometimes it isn't just the mean or the center that you're interested in, but also how variable are these values. And you might make a decision about a measurement that's being taken. You might want to choose the one that has less variability. There's one example in the book about the stock market, right? If two stocks have approximately the same mean, but one is much more variable day to day than another, which one would you rather invest in? Depends on how risk averse you are, right? The one that's more variable is more volatile. Day to day it fluctuates a lot, right? So there's a lot of risk involved there. The one that's less variable is more stable, but probably doesn't increase as much, right? So when we look at, let's pull up our survey data that we collected. Let's see here. This is female heights. And it has the bell-shaped normal curve superimposed over the top of it, just to help illustrate. Actually, I'm going to turn off the tools over there, and then we'll get a better view of this. There we go. Now, actually, if I can put that up where I can draw on it, that'll help. You can look at this data and see that the smallest value in the data set, I'm actually not sure what's going on there, but 56 was the smallest value, and 56 is the right boundary, so this is 56 here, right? And there were two women that were 56 inches tall. How tall is 56? 4'8", right? So 4'8". And then on the upper end, this is 73. So the first measure of spread is very simple. It's called the range. What do you think that is? Okay? The range is just how far. So the range is max minus min. Right? Pretty straightforward. But I'll admit, when I use the word range with non-statisticians, I don't typically just give them a single number like this would be. All right, let's go ahead and compute this. We have a 73 for the max. We have 56 for the min. What's that difference? 17? Right? 17? Check my math always. Right? But if I was talking to my mother and she said, well, what's the range of heights? And I said, 17. She'd go, what? If I said, oh, the range was 56 to 73, she'd understand that. So I tend to use the word range by saying the min and the max rather than the difference. But technically, in statistics, that is the range. Right? So the range is 17 inches. Now, we talked about the mean and how the mean is not resistant to outliers. If you have an outlier in your data, it'll affect the mean, right? What about the range? Would it be resistant to outliers or not resistant to outliers? Not. Right. Why would it not be resistant to outliers? What are the only two data values that get used in the calculation? The outliers, right? So the two most outlying observations, so the range is highly susceptible to outliers. If I had two sets of data, and this is a number line, it doesn't matter what the numbers are, but this is a really fast dot plot, right? So I have one set of data above the line that looks like that, and I have another set of data that looks like this. Which one has more spread? Duh, the one down here, right? What if I add one outlier to that upper one? Which one would you say has more spread?
The bottom one.
Still the bottom one. But what would the range be for both of them? The same, right? Because this outlier now makes the minimum, the max minus the min, equal the max minus the min of this data set. So the range isn't a great measure of spread. It's one we almost always would report. In a table, when I'm reporting summary statistics, I'll always give the min and the max, right? But we need a better one. So the most typical one that you'll see reported is known as the standard deviation. The standard deviation has a nasty looking formula, but that's okay. You're learning to handle that. First of all, the word deviation means deviation from the mean. How far do subjects deviate from the mean? Right? And then what do you think the word standard means? The standard amount of deviation. What do you think they're getting at?
Basic requirement.
Well, that's not a requirement, but yeah, the basic amount of deviation. Right? And I'll show you why in a second. But what we would like to say is the average deviation. On average, how much deviation is there from the mean? But the average doesn't work. So they had to do something different, and then they named it standard deviation. So here's how it works. We'll have two versions of this, the population standard deviation and the sample standard deviation. And the notation that we'll use is the lowercase sigma. Remember I talked about that a little bit last time? Lowercase sigma. And I'm going to put a little sub x on it because your calculator will have that sub x. But remember, x is just a placeholder for variable name. So this just means the standard deviation of the variable x. But if it's a y or a z, you just use that letter. And then sample standard deviation. Do you remember from looking at your calculator what symbol it uses? No? That's okay. S. X. Right? So Greek letter for a population parameter, regular letter for a sample statistic. Right? So parameter means it's a characteristic of the whole population, and it's generally unobservable. So almost never this semester will we be trying to compute the population standard deviation. But it's useful to start there with the formula and then move to this one. All right? So let me leave that there, and I'm going to do this. Population standard deviation. The first thing we need to do is we need to compute the deviation from the mean for every observation. Right? So for every value x in the data, how far does it deviate from the mean? Well, that's just the difference, right? So it's x minus mu, where mu is population mean. So far, so good, right? And then if you want the typical or average amount of deviation, you sum those up and you divide by how many you summed up, right? So what's the symbol we use for summation?
Sigma.
The capital sigma. So sigma. So we're going to add up all the deviations, and then we're going to divide by how many we added up. Now, if I'm doing this for the whole population, remember what symbol we use for the population size? I just threw it up there one time last hour. But remember, for sample size, what do we use? Have I mentioned that the final is comprehensive? N, little n, right, is sample size. And so for population size, big N, good, big N. Right? So that would be the average of the deviations. But there's a problem with this formula. It's not real obvious when you look at it, but algebraically you can prove that if you sum up all of the deviations, they will always sum to 0. Why is that? What's the definition of the mean? Or how is the mean computed? You sum up all the values, you divide by how many you added up, and so it's kind of in the middle, right? So when I take x minus the mean, if you're bigger than the mean, you'll have a positive value. What if you're smaller than the mean? You have a negative value. What happens when you sum up a bunch of positives and a bunch of negatives? They're going to add to 0. And they'll add exactly to 0 because that's how the mean's computed. It's the one that makes, it's right in the middle, right? So this won't work. Then why'd you put it on the board? Well, because all we got to do is get rid of the negatives. Now, in mathematics, how do you get rid of negatives? What'd you say? Not square root. We're going to do that in a minute, but square. If you take a negative and you square it, what do you get? If you take a negative and square root it, what do you get? You have to be a math major to know this. What? Undefined. You can't take the square root of a negative. You get an imaginary number, right? So anyway, so we're going to square them. Now, nobody said it, but you could have also said, oh, to get rid of the negative, you take the absolute value. And that would actually work. And that's another measure of spread. It's called the MAD. I like it for its name, the MAD. The mean absolute deviation, MAD. But it's not taught in our book, not taught in most intro books, because it doesn't get used in practice very often. The standard deviation gets used all the time. Now, we're almost done with this formula, but not quite. We've got to do one more thing. Square root. And why do we want to square root? After we get done summing, we square root. Why do you think we do that? Because you squared them to start with, and so you don't think about units in science class, right? If I'm measuring heights, my units are inches. So I don't want to report the spread in squared inches. Oh, there's this many squared inches. Nobody knows what a squared inch is, right, in terms of height. So we take the square root to put it back into the original units. Okay? Back into the scale that we started with. All right? So that's the formula for standard deviation of the whole population. Now, there's going to be a wrinkle here. When I do the that's an S. It doesn't look like a very good S, but when we do standard deviation of a sample, it's almost identical. We're going to sum up the deviations from the mean, but if we took a sample, that means we don't know the mean of the population. So what do I use instead of mu? Here's a hint. All semester, the rest of the semester, whenever I ask you, what are we going to use when we don't know the population value? The answer is the sample one of those, right? If I don't know the population mean, I'm going to use the sample mean, right? So the sample value of the sample statistic is always going to be the answer to that question. So instead of the population mean, we're going to use the sample mean. We still have to square it for the same reason. And we still divide by the sample size to make it an average squared deviation. But there's one little wrinkle. We don't divide by n, we divide by n minus 1. And there, I could do a week's worth of lectures just on why it's n minus 1. But I'm going to tell you just intuitively why it's n minus 1. And then a quick demonstration of a concept known as degrees of freedom. Okay, and we're going to hit that later in the semester. But you divide by n minus 1 when it's a sample standard deviation intuitively, because when you draw a sample from the population, it's very unlikely that you got the biggest value in the whole population or the smallest value in the whole population, right? Your sample probably didn't get the most extreme observations. So it's going to underestimate the total amount of spread. So to offset that, to make it be a better estimate of the population standard deviation, we need to make it a little bit bigger. How do you make a fraction bigger? You make the bottom smaller. And it turns out if you make it smaller just by one observation, its expectation is exactly the population value you're trying to estimate. Okay? Now this is actually taught later in the book, but it's hard for me to go through this discussion without it. We'll hit several times this semester a concept called degrees of freedom. Okay? And degrees of freedom has to do, well, let me just do an example. Let's make up some data. Right? Small data set with 4 observations in it. And let's say that X bar is 10. Okay? So, what's your first name again? James. Give me the first number. Any number you want. Make up a number. 15. Good. That's a great number. All right? Kimmy, give me a number. Any number you want. 50. All right? Good. Let's see.
36.
What's your name again?
Haley.
Haley, that's right. What did you say?
36.
36. Okay? And
Shatali.
Shatali, I was going to say, you got a hard name.
Shay.
Shay. Okay, I like that. Shay. Give me a number.
24.
24 won't work.
5.
No. We got to get X bar equal 10. See, I set her up for failure. I apologize, but I could tell you could take it. That's why I picked on you. What happened? To get this mean to be 10, what does the sum of the 4 have to be? How do you compute a mean? You add them up and you divide by how many you added. 4. So what divided by 4 gives you 10? 40. these have to sum to 40 to get a mean of 10. So the first 3 people could throw out any number they wanted. But poor Shay, she was out of degrees of freedom. There were no degrees of freedom left. So there's 3 degrees of freedom in this n minus 1. All right? So what number does have to go there? You guys threw out such big numbers, it's going to have to be negative, isn't it? To get it to sum to 40, this is 65, negative 61. Now you'd get a mean of 10. See how it works? So you divide by the degrees of freedom because x bar has already been determined. Once x bar is determined, you're not summing up n independent things. You're summing up n minus 1 independent things. Right? So this is the degrees of freedom, not sample size. If you're measuring the whole population, you don't have to worry about that because the mean has not been computed. It's a fixed number, right? It's a parameter. So you don't lose that degree of freedom. Okay, kind of a long discussion there, but that students, at least me as a student, I hated when somebody just gave me a formula and I said, well, why is it that? And just accept it. Right? It's just that's what it is. It's what the book says. Yeah?
So just by looking at those 4 numbers, how would you know that there's 3 degrees of freedom?
It's just, if I'm going to estimate the mean and fix it in advance, then there's 3 numbers that could be anything we want. But once 3 of them are fixed, then the 4th one cannot be any number. It's got to work. Right? But if I fill in just 2 of them, I still have 1 degree of freedom left to go. Right? I don't have to use special values for both of those. Right? So it's just how far can you go? How many blanks can you fill in with any value at all before you're now stuck? And you can do 3 of them before you get stuck with having to do the 4th one. Okay?
So was the n be 3, like for that particular example?
The n was 4. There were 4 blanks, but n minus 1 was 3. So there were 3 degrees of freedom. So 4 minus 1 equals 3 degrees of freedom. If my sample is size 50, then I got 49 degrees of freedom. So I'm going to divide by 49. Okay? Now, standard deviation is nice. Actually, this is called being indecisive. I decided I don't want to erase that because I'm going to be pointing at it. But I don't want to bar down the middle of my thing here. So look at the graph of female heights. Right? Do you remember what the standard deviation was? I showed it before and we talked about it, but I don't know if you remember. Anybody remember? All right, I'm going to show you again. From now on, memorize this. I'm kidding, you don't really have to memorize it. There it is. So for female heights, mu was 65.27, the mean. Right? Now it would be mu if we're considering that these are the only females in the whole world. Right? This is the population. It would be sigma for standard deviation. Right? If this was the whole population. But really this is x bar and sx. But it's 2.95. So we'll round. That's about 3 inches. So the standard deviation is about 3 inches. Okay? Now, back to the picture. Actually, this is a better picture. This is all semesters put together. So it's a little smoother. Doesn't really matter. But it has about the same mean. 65, a little more than 65 inches. And a standard deviation of about 3. Now look where 3 is. 65 plus 3 gets you where? 68. Right? So there's 68. And I'm going to draw up to this smooth normal curve. And down 65 minus 3 gets me to 62. So there's 62. Right? So this interval, 62 to 68, is the mean plus and minus 1 standard deviation. Right? Notice where 1 standard deviation falls. When you have a nice normal curve like this, 1 standard deviation is about halfway down the hill. That's technical mathematical lingo. But this is about halfway down the hill. So anytime you have a symmetric and bell-shaped distribution, you can get a pretty good ballpark estimate of the standard deviation by looking at the histogram and saying, well, here's my peak and here's the bottom, about halfway down the hill. How far do I have to go away from the mean to get halfway down the hill? About 3. Oh, my standard deviation is about 3. Right? Now, what percent of females does it look like falls in that range? Well, you kind of have to learn to read these distributions, but remember, this is a percent distribution. If I add up the heights of every one of these red bars, what would they add up to? It's okay, I can wait. What? No, these are percents, but you're on the right idea. What percent of 3,220? 100%. So since these are heights are percentages, like this is 2%, so that bar right there is about 3, maybe 3.5%. If I start adding all those up, they'll add up to 100%. Right? So now, with that in mind, what percent of all the women seem to fall in here? Just think of the whole thing as being the total. How much of the total is in between those two bars? 70%? Really good guess. What did you say? 7.5%. 7.5%? In here? That's...
No, just that.
Oh, just the middle. Yeah, in the middle bar. No, I mean in this interval. Well, it turns out that that's about 68%. If you have a bell-shaped and symmetric distribution, about 68% of all subjects will fall within 1 standard deviation of the mean. So it's right about 2/3. 2/3 is 67%, right? So this is something known as the empirical rule. Now this works with population parameters, mu and sigma, or with x bar and sx. Either way works. So, but I'm going to do it with the mu's because they're easier. Mu plus and minus 1 standard deviation will contain about 68% of the population. Right? So that's 62 inches to 68 inches tall. Now, we have more females in here than males, so that's why I use females. Raise your hand if you fall into that range. Raise your hand if you're between 62 inches and 68 inches tall. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So 10 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 females. So we had 10 out of 22 females in this class. What is that? Do that on your calculator. 10 divided by 22.
0.45.
What?
0.45.
0.45. Well, it didn't work as good as I had hoped. But you would expect, when you have really small samples, you can't expect it to be perfect. But let's now go one more standard deviation. Add another 3 to 68. What do you get? 71. So 71 is right there. And subtract another 3 from 62 and you get 59, which is right there. Look at the graph. About what percent of the total area does it look like falls between those values? 90%? It's even a little higher than 90%. It's 95%. So mu plus or minus 2 sigma contains about 95%. Raise your hand if you're between 59 inches tall, which is 4 foot 11, and 71, which is 5 foot 11. Raise your hand if you're a female and you're in there. 1, 2, 3. Nobody didn't raise their hand. 100% of you, right? So we got 100% that fell in here. Pretty close to the 95%. Right? All right. When I combine all semesters together, I have a huge sample here. Notice there are some women that are taller than that. And there are some that are shorter than that. Let's go one more standard deviation. 71 plus another 3 inches is 74 inches right there. And 59 minus 3 is 56 right there. Right? What percent does that look like? It looks almost like 100%, doesn't it? And it is almost 100%. Mu plus or minus 3 sigma will contain approximately 99.7%. Or as my mother would say, pert near everybody. Pert near everybody in the population will fall within 3 standard deviations of the mean. Did you have a question?
Yeah, how do you know to, like, plus 3 on the highest and minus 3 on the lowest? Like, why 3, not 2, or?
Because that's the standard deviation. And I didn't remember to write that up here, but mu is 65. I'm rounding, but mu is 65 and sigma is 3. So when I plug in the 3 here, let's do the numbers. This is 65 plus or minus 3, which gives me the interval 62 to 68. And then this one is 65 plus or minus 2 times 3, and so on. Right? So when I go 3 times 3, that's 9. So I go from 65 plus 9 would give me 74. Got it? Okay, so I didn't finish my picture here, but that's 95% stopping there. And stopping here is 99.7%. Okay, and that's known as the empirical rule. There is another rule for distributions that aren't bell-shaped and symmetric, but I'm not going to hold you responsible for it. It's in the book, but I've deleted it out of the homework lesson over this. But I will mention it. It bears mentioning, but not a whole lot else. It's called Chebyshev's theorem. And that's the way I abbreviate theorem. So Chebyshev's theorem works for any distribution, not just bell-shaped and symmetric distributions. But I've been a statistician now for over 20 years, and I've yet to ever really need to use Chebyshev's theorem. So I don't think it's all that important, right? So we'll skip this. It's in the book and all that, but we'll skip that. Okay? All right, well, what I want to do next is I want you to get your calculators out, and I'm going to pull up this picture. This is in the slideshow, the PowerPoint slides over this section, which I have already posted for you out on D2L. If you're interested, you don't have to get them. But we're going to practice this formula using a made-up data set of only 5 things. And we'll see how to compute this by hand. And then we're going to do it with our calculator.
I have a quick question about the empirical rule.
Okay?
So if we get like a problem, like in the homework, like a question, and we have like the bar, the histogram, and so do we like just keep going to like 4 sigmas till the time we reach close to 100? Would it always be like 3s?
Once you get to 3, there's really nothing left. So going to 4 is probably not going to be important. But the kind of questions they're going to ask you on the homework, they'll ask it in either direction. They'll say, find an interval of values that should contain 95% of all women. And then you do, well, that's 95% goes with 2 standard deviations. So take the mean, add and subtract 2 standard deviations, and there's your interval. Right? And then they'll give you an interval or a number, and they'll say, what percent of women should fall in this range? And so then you have to figure out, well, how many standard deviations is that? Right? And once you know, oh, that's 3 standard deviations, then 99.7% of women should be in that range. Right? That's how they're going to ask you empirical real questions.
So it's always that particular percent that fall in the range?
Yeah. Always is a strong word for a statistician. Most of the time. And notice that they don't use the word exact. They say approximately 68%, approximately 95%, and so on. Later in the semester, we'll firm it up and make it more exact, but these won't be nice integer numbers. They'll be numbers close to that. But okay, so now, the easiest way, if you have to do one of these by hand, is to make a little table. Make a column for your x variable, and compute the mean. And then make a column for x minus the mean. So obviously the mean of these numbers is what? Obviously it's 7, because they've used a 7, right? But you could do it in your head probably. 13, 20, 35, divide by 5 would be 7. Right? So the mean of this data is 7. Now, since they made this data be real special and easy and have all integer values over here, it works out really nice, but these could be anything, and it still works. You just need a calculator to do it. You wouldn't be able to do it in your head. Now, notice 7 is the mean, and it's right here in the middle. Right? These have been put in order. What's the typical amount of deviation from that mean of 7? Both of these are how many units away? 1. Right? And then both of these are 2. So the typical amount of deviation, I got 2 2s and 2 1s and a 0, because 7 is 0 deviation from the mean. Right? So I got 1 0, 2 1s, and 2 2s. The typical amount of deviation, I don't know, 1 point something. Right? I'm just kind of mentally averaging those values. So 5 minus 7 is negative 2. Then you square that to make it fit the formula. Negative 2 squared is 4. 8 minus 7 is 1. Square it, you get 1. 7 minus 7 is 0. We get a negative 1 squared is 1. And another 4. So now what does this symbol say to do? Sum them up. So I have a column that is each x minus x bar quantity squared. Now I'm going to sum them up. So sum this column. What do they add up to? 10. Right? Okay, we're almost done. 10 divided by, what would this be? How many data values do we have? 5. So n minus 1 is 4. So I've got, under my square root here, I've got 10 over 4. 10 divided by 4 is 2.5. So I need the square root of 2.5. Do that on your calculator. I can't do that in my head.
1.58.
Actually, I can do it in my head. I just don't want to show off.
1.58.
1.58. Okay? 1.58. And that's rounding to 2 decimal places. Right? Now, I forgot to look it up before I came to class, so I'm going to try to do it right now. But I saw in the homework, when I was getting the homework questions picked, I saw some of them say, use the rules for rounding standard deviations. And different books have different rules. But here it is on page 148. It says, rounding rule. When calculating the variance, round to one more decimal place than the largest number of decimal places in the data. Huh? Use one more decimal place than the data has. Right? They say the largest amount in the data, usually the data will all be to the same number of places. But if not, then if one of them goes to 3 places, then you gotta go to 4. How many places do we have here? 0 decimal places. So I need to round to 1 decimal place. 1 more than 0 is 1, right? So we would round this to 1.6. Right? Okay, so if I page down, they should have that answer. Square root of 2.5, 1.58 rounds to 1.6. Right? Now, take those same 5 numbers and put them in a list in your calculator. Put them in L1 in your calculator. You probably need to see the numbers, don't you? There they are. 5, 8, 7, 6, 9. Put those in a list. Okay, everybody got that? Now, do you remember how to compute summary statistics from a list? We did this last time to get the mean. You did exactly the same thing to get the standard deviation. Do you remember what it was? 1 var stats. And you get there by stat button. Actually, it's on the slide, so I don't have to write it on the board. Right there. Press the stat button. Then go to edit and press enter. Enter the data into L1. Press stat again. Go to calc. Select 1 var stats. Now, depending on how new your calculator is, you then either enter the list colon L1, freq list, leave it blank, because there is no list of frequencies that we're worried about, and then calculate. If you have the older style, you're just going to do 1 var stats, L1, enter. So, did you get this number? Tell me what you did get, because your calculator would have given you both, sigma x and sx. What did it give for sigma x? 1.41. Okay? And then you got this number for sx. Everybody got that? What's the difference? Don't be a smart aleck and go, well, the difference is about 0.17. Why are they different? What does your calculator do to compute this one? And what does it do to compute this one? What did you say?
It's n minus 1.
It uses n minus 1 for this one, and it uses n for this one. You would use this one if those 5 values you entered are the only 5 in the whole population. So if you have the data on the entire population, then this is the one you want to use. Almost always, it makes more sense that it's a sample from the population, so you can use SX. The only time we'll use sigma x all semester, pretty much, is when we do probability distributions. And that's coming right up, by the way. Okay? Questions about that? All right. One term that I read as I was doing the rounding rule that reminded me, the variance is another measure of spread. The variance is sigma squared, or SX squared. So all it is, the variance is the number you get before you take the square root. They call that variance. And then when you take the square root, they call it standard deviation. So variance is standard deviation squared. So on the homework, there's a couple of times when they ask you to compute the variance. You just do your 1 var stats, get your SX, and then take that number and square it. You'll have the variance. Everybody hear that? That's what I thought. You do your 1 var stats, you get the standard deviation, and then you just take that number, type it in, and square it, and you'll have the variance. Okay? Your calculator will not automatically give you the variance. Okay? Then one more topic that we need to talk about, and then we'll be done. It's called the coefficient of variation. And I think there's a right there. This is called the coefficient of variation. And what it does, all the coefficient of variation does is tell you how big the standard deviation is. In other words, how much spread is there relative to the mean. So it just takes the standard deviation and divides by the mean. Then it multiplies by 100 to make it a percent. So what percent of the mean is the standard deviation? That's called the coefficient of variation. And the reason you would compute that is it can give you an idea about skewness. Right? If your standard deviation is bigger than your mean and you can't have 0 or negative values, then you know you've got skewed distribution. Right? If you have a wall at 0 and you have a skewed distribution, here's the mean, probably about right there. The standard deviation is going to be pretty close to as big as the mean is. So you have a big coefficient of variation. Oh, I've probably got skewness here. Because in a skewed distribution, one tail kind of gets lopped off. Right? So you can't spread in that direction, so your standard deviation is as big as your mean is. Okay, so let's do this coefficient of variation for the female heights. For female heights, the coefficient of variation is what? Use that little formula. Now, I'm depending on you memorizing what the mean and the standard deviation were for female heights. What was the standard deviation? No, that was the 1.6 was the made-up data we did.
2.97.
Okay, but we rounded to 3, right? So we had standard deviation of 3 inches for women, divide by the mean, 65 inches, multiply by 100%, or multiply by 100 to make it a percent, and what do you get? 4.6%. So the standard deviation is only 4.6% of what the mean is. Right? So that's a very small coefficient of variation, which basically says you've got a lot of room before you get to 0, because you can't have negative heights. You've got a lot of room before you get to 0 in terms of where the mean is to get the standard deviations in. The standard deviation is a very small percentage of the mean. Right? But if we did age, we would see that it's really big compared to what the mean is. Okay? All right. Well, have a great Labor Day weekend. Study statistics at least 4 hours each day, and you'll be ready to roll on Wednesday. This homework, there are actually 2 homework sets over 3 too, but I got through both of them. So both of them will be due next, well, it won't be Friday. It'll be due next Friday, a week from today. Because Wednesday is our next class.
So you'll have them both online, so you can...
Yeah, they're already there.
They are?
Yeah.
Okay.
I just put them up right before class.
Okay. I have a question.